Hello everyone, welcome to topic 5.4, elementary reactions. By the end of this, you should be able to represent an elementary reaction as a rate law expression using stoichiometry. These are going to be built upon as we head into reaction mechanisms and steady state approximation, so make sure that we are paying close attention. An elementary reaction is a single step reaction within the reaction mechanism. Consider the reaction below, where we have nitrous oxide reacting with oxygen to produce nitrogen dioxide. It is very unlikely for three particles to collide at the same time and in the correct orientation for a reaction to occur. It's highly unlikely, statistically dang near impossible. This reaction actually takes place in two steps or elementary reactions. So noting that steps in a reaction path or process are called elementary reactions. First, the two nitrous oxide molecules react to form an unstable intermediate, dinitrogen dioxide, which is shown here. So this is the first elementary step. Then dinitrogen dioxide intermediates react with the oxygen gas to form the final product, so that this is another elementary step. So these are our elementary steps. And then the net equation is formed by combining these two reactions and canceling out the intermediate dinitrogen dioxide, and you end up with the overall reaction. It is important to notice that the sum of the elementary steps is the same as the overall balanced equation. Okay, so your reaction mechanism, which is these two are going to add to give you your overall balanced equation. These two combined are your reaction mechanism, and each one of these is called an elementary step or elementary reaction. The term intermediate describes a species that is neither reactants nor products. They are formed during the reaction and then are consumed by the reaction. So they are first made and then they are used again. They also tend to be highly unstable and so react very readily. The molecularity of a reaction, say that 5 times fast, describes the number of molecules that have to collide in an elementary step. So both elementary steps above in this reaction mechanism that we were describing are bimolecular, right? Because two different molecules, and even if it's the same one, it's two molecules are colliding. Unimolecular molecules involve only one particle, and that might be like decomposition, nuclear decay, or isomerization, which is where like a group moves from one spot to another on a molecule. This is very important in organic chemistry. And then termolecular reactions involve 3 colliding particles. Termolecular are very rare because it is highly unlikely for 3 particles to collide simultaneously in the correct orientations. And don't forget, with enough energy. You can know how difficult this is if you have ever attempted a 3-person high five. I did not come up with that analogy. The rate law can be inferred from an elementary step based on the number of particles that must collide. For example, in the reaction above, the rate law of the first step would be rate equals K times the concentration of nitrous oxide squared. There are 2 particles of nitrous oxide that must collide, so it is second order. The rate law for step 2 would be as follows. So it is important to note, and you see that here, is that for elementary steps, the rate law mirrors the stoichiometry of the elementary step. but not the overall reaction. Okay. Sometimes you are given information about the speed of an elementary step in the reaction. The slowest step is known as the rate determining step because you can only go as fast as your slowest part. So like me trying to walk my kids somewhere, we can only go as fast as the slowest member, which usually is my 5-year-old. So yay, way to go, Owen. So this limits how fast the reaction can go. So you can only walk as fast as the slowest person in your party. They're gonna like slow everybody else down, even if you tell them, hurry up, let's go, let's race. Nope, nobody wants to race. Imagine that you work in a chocolate shop. Chocolate. It takes you 15 minutes to make chocolate, 8 hours for it to cool, and 5 minutes to box it. The step in this example that limits how fast you can make the chocolate is the cooling step. You can't really speed it up, it has to actually cool. And speeding up the other 2 steps, making the chocolate or boxing the chocolate, doesn't impact how long that reaction takes significantly. So you are always limited by the slowest step. So the slowest step of the reaction determines the rate of reaction. If the first step is slow, then the overall rate for the reaction will be based on the stoichiometry for the first elementary reaction, which we mentioned above. So it is important to note here that the slow step determines the rate, and that includes the rate law. Okay, so for this one, our first step is slow, so our rate is this. If subsequent elementary reactions are slow, so in this one, then you have to add all the reactants up to the slowest step and cancel any intermediate that in order to determine the rate of reaction. We are going to come back to this. In 5.9, where we talk about the steady state approximation. Okay. So we aren't going to look at how do we do this yet, because notice this does not mirror your slow step. There's a way to do it, but that is for a later video. Okay, so let's look at how we can do this. Given the following elementary steps, what is the overall reaction and what is the rate law for the elementary step 1? And so the first one is always step 1, just so that we remember that. So we are going to look at the overall reaction first. So when we want the overall reaction, we're going to cancel anything that's on both sides. So these cancel, kind of like net. And so we write what's left over. So 2HI gas is going to yield hydrogen gas, and iodine gas. Then writing the rate law for step 1, it always takes the form of rate equals K times something, and that's going to be our reactants. And because it's an elementary step, we use the stoichiometric coefficient to give us the order for that. So it'd be 2. So this is our rate law. Okay, for our redo, gaseous cyclobutane, C4H8, breaks into 2 gaseous ethylene molecules via single-step unimolecular reaction. Write the balanced equation for this reaction, and then write the rate law for the reaction based on the stoichiometry of the first step. So this is actually going to be where, since it tells you it's a single-step unimolecular, that means that this is the only reactant because it's a unimolecular. Single step tells us that the elementary step is the final balanced chemical equation. So C4H8, and it tells us it's a gas, breaks into, so changes into 2 gaseous ethylene molecules. So C2H4, and that's a gas. So this is both our balanced equation, like for the full reaction, and our elementary step. So we wrote the balanced equation. Now we're going to write the rate law. And so rate is equal to K times the concentration of C4H8. And there's no exponent, but you can write a 1 because stoichiometry says that that's a 1 there. But I don't like writing the 1s. So we can do this only because the balanced equation is the elementary reaction as well. So make sure you aren't always assuming for balanced reactions that the balanced reaction represents the rate law. It will most of the time not. Okay, as we see above. Okay, so that concludes the we do. Practice with the you do's, check your work, and thank you for tuning in.